source conversions, Y, and delta transformation as well. So again, so far the symbol we've been using is mainly we've been using this symbol for a DC voltage source, right? This is what we call an ideal source, right? Or a perfect source. We are saying that this source has no load resistance, right? So in other words, when we to any component in the circuit, this source appears as just there's no resistance across it. This is the perfect component. So if you look at this graph here, we'll look at the blue graph here. This represents an ideal source. It says that it doesn't matter how much current is coming out, the voltage is always going to stay the same for this source. There is no internal source resistance. Okay, this is the perfect source that we like to start using to analyze circuits, but in the real world, we actually have there is actually a resistance inside of our source. We call that the internal resistance. So the source, the real source, we call it a practical source or a non-ideal source, is one where we actually have a source resistance. So there is a resistance that another component sees when it looks at the power supply. It doesn't only see the supply, but it sees a resistance, right? And as a result of that resistance, what happens is that 100% of the voltage generated by the source does not get to the load. So if we call this a load here, let's put a resistor here and call it a load, RL. So because of the source resistance, 100% of our current voltage does not get to the load, and so some voltage is dropped across this resistance. So again, the more the voltage increases, the more voltage drop we will have across the source resistance. And so this is what we see in this graph here. Of course, keep in mind that this graph is from 0 to 6. I think here we're using a source resistance of 0.2 ohms, right? So what happens here is that as we increase the current, this more voltage is dropped across our source resistance inside of our meter, and so less voltage gets to the load, right? So you can see here as the current increases, then the voltage of our power supply is dropping. So it's no longer 5 volts. It's going to be reduced because the rest of that voltage is dropped across the source. So just like the voltage divider, if you want to find out what the total voltage is across the load, it's going to be RL over RS plus RL times whatever voltage your power supply is giving out. So the proportion of the voltage that is coming out of your supply is the load resistance over the source plus the load times Vs, right? And again, we are saying that as the current increases, you should expect that this source, the voltage dropped across the source resistance will also increase as well, okay? So this is the ideal source, right? We are saying that the voltage is always the same, but in the real world, like I said, for battery, as you use the battery, when you draw more current from the battery, the voltage will be reduced. Even a power supply, if you increase the current that you're drawing from the power supply, the voltage will also reduce as well. Okay, let's talk about the current source. Now, a current source is a power supply that supplies a fixed amount of current to a circuit. So let's look at this circuit right here. This is a symbol for DC current source, and what the current source does, it keeps the current fixed. So let's say we have 1 ampere of current coming here to this load, and this load is a 100 ohm resistor. This is the current source. We have to program. We just tell it the current to supply, and it's going to supply that. So now we can find out what the voltage drop is across this. V is going to be equal to I times R. So with the voltage source, you set the voltage. With the current source, you actually set the current. So we know that the voltage is going to be 100 times 1 ampere. 1 ampere times 100, which is going to be 100 volts. Of course, the voltage source has limitations as to the maximum voltage it can go to, but it's going to change the voltage to maintain a fixed amount of current coming out of it, right? So again, if you think of Ohm's law, V is equal to I times R. If you want to, if one of these is fixed, like if we keep the current fixed for the current source and the load is fixed, we need to change the voltage so that our current stays as it needs to be. Now, of course, this is the ideal source, so we have no source resistance. And so it doesn't matter how much voltage we are drawing from this current source, the current is staying fixed at 5 amperes, right? Now, this is the ideal source. But in the practical world, in the real world, the current source doesn't keep the current at 5 amperes because there is actually a source resistance in parallel with the current source, and some of the current goes into that source resistance, right? So if this is our load here, all the current doesn't go to the load. Some goes to the source resistance, right? So again, we expect that some current will go here and the rest will go to our load. So the total current that our source is putting out is not going to the load, but some is going to that source resistance. And so if you wanted to find out the current that is coming out to our load, we can also calculate it using the current divider. So that current I that is going to our load is going to be equal to RS over RS plus RL. Now, most times the source resistance is very large. So you can just imagine that the source resistance is infinity for the practical source, right? If it's ideal, imagine that the source resistance is infinity, right? So it means that all the current is going in our load, right? But in the real one, of course, it has some practical value times. So again, if you wanted to calculate that the load resistance is going to be the source resistance over source plus load times IS. Now, if for the ideal source, we are saying that the source resistance here is infinity, so it means that all of that fraction would be like 1. So our load is going to be the same as the source. Now, if you look at here, ideally, we want to say that in the ideal case, the source resistance is equal to 0, so that no voltage is dropped across the source and all the voltage is across the load. So this is just a short spiel on ideal and practical sources. Now, of course, we will have some problems where we will ask you to use a practical source in your calculations. So again, with here, we know some current is going here and the rest of the current is going there. Now, there's one thing called maximum power transfer, and this is where we want to have, for maximum power transfer, we want to have the source resistance being equal to the load, right? So this will come up again in your electronics training. Maximum power transfer. Okay, we want to have RS equal to RL. Okay, especially when you talk about antennas, when we design antenna systems, we want our source resistance, which is the resistance or the impedance of our power supply or our signal generator, to be equal to the impedance of the load, to be equal to the impedance of the transmission line, so we can have the maximum amount of power going to our load where we will have our signal being radiated out. So again, for maximum power transfer, RS should be equal to RL. Okay, let's go on to talking about the Y and the delta transfers, right? And the current source to voltage source conversions, right? So here's an example. Let's talk about the conversions first. Sometimes it's important to convert a voltage source to a current source. So let's say we have this voltage source right here, right? And we have a source resistance. And this is our voltage source. Maybe it's connected. Let's say our source resistance RS is equal to 0.5 ohms. And the voltage source is equal to 10 volts. And if you're told to convert this to a current source, what would you do? Well, you would need to multiply the source by the multiply. So again, remember that I is equal to what? V over R, right? So if you want to convert this to a current source, you can divide the voltage by the resistance. So we get here 10 volts over 0.5 ohms. That will give us 20 amps. So the current is going to be 20 amps and the resistance is going to be the source resistance. So how do you draw this? Well, you draw a current source, you put 20 amps here, and then you also draw the source resistance and you use the same RS for the source resistance, 0.5 amps for the source resistance, right? Now let's connect a load to this and see if we get the same value for our load. So let me change the color. Let's connect the load to these two circuits and see if they're the same. So let's connect say we'll connect a 5 ohms resistor here, 5 ohms. And we want to know, okay, well, what is the voltage across this 5 ohm resistor? Well, of course, we sort of see what's going on right here, that we have 2 amps coming out here. Now some current will go here and the rest of the current will come there. So we want to find out, okay, what is the voltage that's going to be across this 5 ohms? How much current is going to go there? So to calculate this, let us use the current divider equation like we just saw. So we can say that IL, which is our load, IL is going to be equal to RS over RS plus RL times our total current, IS. In this case, it's going to be 0.5 0.5 over 0.5 plus 5, so 5.5 times IS. Times 20. Well, this is 20 here. And that gives us all right, this gives us 1.818 amperes, right? Now, if we know that the current here is 1.818 amperes, we can find the voltage. VL is going to be equal to I times R, which is going to equal to 5 times 1.818, which gives us 9.09 volts. So this is the voltage across our load based on the amount of current that is flowing through it here. Let's do the same thing for our current, for our voltage source over here. What if we connect our 5 ohm load across it? 5 ohms, right? What's the voltage going to be across our load resistor, right? This is what we want to find out. So to do that, of course, we're going to use this equation that we looked at right here using the voltage divider equation. So I'll do it right here. On this side, we have our VL is going to be equal to 5 RL over RS plus RL times VS, which is equal to 5 over 5.5 times 10. 5 over 5.5 times 10. So that gives me 9.09 volts. So you can see that the voltage is the same after the source conversion. Let's do another example. All right. Okay, another example of the source conversion. Say we are given this current source right here. And this current source is applying, let's say it's applying 1 amp. And say our source resistance is 10K. All right, so this is our current source. And say we are told to convert this to a voltage source. And say the load across it is 10 ohm load. All right, this is our load. And we're told to convert this to a voltage source, Okay, so what do? Convert it to a voltage source. Of course, we know that V is equal to what? I times R, right? And so we need to multiply. So to get the voltage source, we need to multiply the current source, which is 1 ampere, times the RS, which is going to be 10K. And that gives us 10,000 volts, 10 kilovolts, right? So to draw this, we just draw a source here representing 10 kilovolts. Of course, we need to have a source resistance of the same source resistance, which is going to be 10K. All right. Now, if we're to connect the load across this, we want to verify that this is going to work, that we're going to have the same voltage across our load. We can find that voltage here. First, let's find the current, and then we have to multiply the current by the voltage. So IL is going to be equal to RS over RS plus RL times IS. And this gives us here 10K over 10.01K times 1 ampere, which is very close to 1 ampere. 10,000 divided by 10,000 and 1. 10,010 and that gives me 0.9999001 ampere going for our load. So we can find out our, so using Ohm's law, we can know that VL is going to be equal to I times R, which is equal to 10 ohms times 0.99901 amps, and that gives me 9.99001 volts across my load. All right, so this is the voltage across the load for this current source. Now let's do the same thing on here, where we're going to connect the load to it. Again, we have a 10 ohm load. So now we can find the voltage directly using the voltage divider equation. VL is equal to RL over R1 plus, over RL plus RS, RS plus RL times VS. And of course, we're going to have here what's it, 10 over 10.01K times 10K. And that gives again 9.99001 volts. So it's the same. So source conversion is not difficult at all. You just use Ohm's law. If you're going from current to voltage, you need to multiply. If you're going from voltage to current, you divide, and so forth. Okay, let's talk about Y delta conversions quickly. So what is Y and delta conversions? So we have some arrangements of resistors in some circuits that we need to change so that we can solve the problems. So again, you will see later on in the course, we will have some problems to solve. And so these examples are just ways that we can solve this problem. So we may have to do a Y delta conversion so that we can obtain our solution. So a delta is where we have three resistors connected together. And you cannot really definitely say that they're in series or they're in parallel. All right, and so you may need to convert them to be able to solve the circuit. So let's call this one RA, RB, RC, and they are connected at one point here, another point here, and another point here. Right, so we may need to convert this into another form so we can solve the problem. Right, so to convert, we want to convert it into this form right here, which is called the Y form. So we have here R1, R3, R2, and of course connected to points 1, 2, and 3. Now this is very important, especially when we look at power circuits or three-phase circuits. So there are some standard equations that you will use to obtain R1, R2, and R3. So like for here, R1 is going to be equal to RA, because bring it a little higher. So I'm just going to put down the equations quickly. R1 is going to be equal to RA times RC divided by RA plus RB plus RC. Likewise, R2 is going to be equal to RA times RB over the same thing, RA plus RB plus RC. And of course, R3 is going to be equal to RB times RC. Divided by RA plus RB plus RC. So again, these may be useful when it comes to, solving problems where we are told to find, say for example, you have a series parallel combination that has a loop that you cannot solve, then you will use this this Y delta methods to solve it. So we have some other equations to go to the opposite value. So this is to go from delta to Y. What if we wanted to go from Y to delta? So you want to go from the Y to the delta. This is what you would do. Again, this is going to be point 1, 2, and 3. And you have R1, R2, and R3. And you want to go to, so most times when you solve the circuit, you need to put it back how it was. So this is point 3, 1, and 2. And we have RA here, RB, and RC. And so here are the equations that you can use to go between the two. So RA is going to be equal to R1 plus R2 plus R1 times R2 divided by R3. And RB is going to be equal to R2 plus R3 plus R2 times R3 over R1. Likewise, RC is going to be equal to R1 plus R3 plus R1 times R3 over R2. All right, so we've come to the end of another one. This is Prof. Scangrella. See you in the next one.